Hi everyone. Today I'm excited to share our latest research on enhancing the safety of autonomous driving systems. Our paper titled Overcoming Blind Spots: Occlusion Considerations for Improved Autonomous Driving Safety dives into the critical issue of handling occluded areas. At TOM's AVS lab, my colleagues and I have developed an innovative approach to better understand and address the challenges posed by occlusions. In this presentation, we'll discuss the methodology of our research and present our findings on how considering occlusions can improve safety for AVs. So, let's buckle up and take a closer look at the future of autonomous driving. Let's begin by understanding why this research is crucial. The motivation for our work is grounded in the challenges that AVs face, particularly in occluded areas. The graph here shows the 2021 statistics for traffic fatalities in Germany by participant type and location. Notice the significant number of incidents involving vulnerable road users, or VRUs, such as pedestrians and cyclists, especially in urban areas where occlusions are most prevalent. AVs must navigate through these complex environments where static and dynamic obstacles often create blind spots. Our objective is to plan safe and efficient trajectories for autonomous vehicles by effectively addressing these uncertainties. The overall goal is to enhance safety for all road users without compromising traffic efficiency. This means developing a system that can anticipate and react to potential hazards that are not immediately visible, ensuring a safer integration of autonomous vehicles into our daily traffic. On our next slide, we have two compelling video clips that demonstrate the dangers associated with occlusions. These real-world examples underscore the urgency of our research. As you've just seen, these moments highlight what can happen in a split second when drivers' views are obstructed. In the first clip on the left, children emerge unexpectedly from behind a bus, nearly missing an oncoming truck. In the second, a pedestrian crossing the street is obscured by vehicles, almost unnoticed by an approaching car. These are the types of critical scenarios our research aims to address. By enhancing autonomous vehicles' ability to detect and respond to occluded areas, we can prevent such near misses from becoming tragedies. As we move forward, let's focus on the specific contributions of our project, which we call Frenetics Occlusion, to the AV community. First, we've developed a method for blind spot detection. This allows us to model hidden traffic participants as phantom agents. Think of it as giving AVs the power to see the invisible, predicting potential hazards before they become visible. Next, our movement prediction capability. This isn't just about knowing where objects are, but also about forecasting where they are likely to go. Our method evaluates possible trajectories of these phantom agents, enabling a dynamic and proactive safety assessment. And we haven't kept this to ourselves. We've packaged our solution into an open source module now available on GitHub for anyone to use. This module can be integrated into existing motion planning frameworks, giving them a layer of occlusion awareness. Through these contributions, we aim to foster a safer environment for all road users. In order to understand where our work sits within the field, we have looked into existing literature. Existing approaches to model occluded areas include risk assessment of traffic participants, visibility risk evaluation, simulations using particles for occluded vehicles, POMDPs, set-based prediction, and reachable set estimations. These methodologies have laid a solid foundation for understanding risks in occluded environments. However, we have identified some limitations in these approaches. Scalability is a challenge, especially in scenarios with diverse behaviors of traffic participants. Real-time processing demands are often high, making some of these solutions less viable for on-the-fly decision-making. Lastly, inclusivity is limited. There is a need for a more comprehensive consideration for the full range of traffic participants. To address these gaps, we are proposing an open-source adaptable framework. Our goal is to integrate various criticality metrics for a comprehensive occlusion safety assessment, making it possible to tailor solutions to specific environments and scenarios. Let's have a look into the overall framework. Everything happens within a simulation environment where we define the scenario and parameters. This sets the stage for the motion planner, which takes into account the vehicle's current state and creates possible trajectories. Once we have these trajectories, the frenetics occlusion component kicks in. Here we identify potential phantom agents. This involves not just detecting where they are, but predicting where they might move next. After this prediction, we perform a safety assessment. It's like a what-if analysis that evaluates the potential outcomes and risks associated with each trajectory. This safety rating is then returned to the motion planner. Let's now take a closer look at the trajectory evaluation process within our frenetics occlusion framework. This process begins with the identification of potential occluded traffic participants. Here, we calculate the visible and occluded areas, identifying the critical regions where occluded participants may exist. Moving to the prediction of phantom agent movement, our model takes these identified points and predicts possible paths for different types of agents: pedestrians, cyclists, and vehicles. This predictive capability allows us to forecast various movements and their impact on the AV's trajectory. Next, we arrive at metric calculation. We calculate a series of safety metrics such as time to collision, time to closest encounter, and so on. These metrics give us a quantitative assessment of the risks associated with each planned trajectory. Finally, these calculations feed into our safety rating, which is a comprehensive assessment that considers all the metrics to rate the safety of each possible trajectory. It's about making informed decisions to maintain safety as the top priority without unnecessarily hindering traffic flow. After talking a lot about the methodology, we want to look at some results. This slide represents the results from a critical test scenario, an AV making a left turn at an intersection with a truck obstructing the view. The graph illustrates the velocity of the vehicle over the s-coordinate, which represents the path along the road. The different lines show the vehicle speed under varying safety thresholds denoted by Hmax, which is the maximum acceptable harm. As you can see, when Hmax is infinite, meaning there is no restriction on harm, the vehicle proceeds without reducing speed, leading to a potential collision indicated by the red star. However, when we apply stricter harm thresholds, Hmax values of 0.15 and 0.1, the vehicle speed reduces much earlier, allowing it to safely navigate the intersection without an incident. The videos on the right provide a visualization of the black and green lines. They show the occluded area in red and the point at which the bike becomes visible to the vehicle's sensors. Thanks to the frenetics occlusion safety assessment, the simulation with limited harm, so the green line, was completed successfully without any accidents. Building on our previous findings, this slide illustrates additional simulation results, this time a left turn intersection with a car obstructing the view. You'll notice two distinct lines. One represents the vehicle's velocity when the maximum risk, Rmax, is considered infinite, which would be the case without our frenetics occlusion safety assessment. The other line shows the vehicle's velocity when the risk threshold is tightly constrained at Rmax equals 0.01. The dotted vertical line marks the point where the bicycle becomes visible to the vehicle's sensors. With an infinite Rmax, the vehicle continues at a higher speed, leading to a collision, indicated by the red star. However, when the frenetics occlusion is applied with a low Rmax, the vehicle starts decelerating much earlier, successfully avoiding a collision. The simulation results are again visualized on the right. We are now looking at the results from a scenario where our vehicle is executing a right turn with a pedestrian crossing the road, potentially hidden from view. Again, the graph displays the velocity of the vehicle as it travels along the s-coordinate. For h max set to infinity, the vehicle maintains a higher speed and, unfortunately, it leads to a collision with the pedestrian. However, with lower h max values, we see a different outcome. As the vehicle approaches the critical area, the speed is reduced, allowing for the pedestrian to be safely accounted for and avoided. As we look beyond the effectiveness of our frenetics occlusion framework, it's crucial to consider the practicality of its application in real-time environments. This slide provides a runtime analysis for the various metrics we utilize. The bar chart demonstrates the minimum, medium, and maximum runtime measurements for each criticality metric. You'll observe that some metrics, like CP and TTC, are calculated quite swiftly, typically in under a millisecond. This speed is vital for the real-time needs of autonomous driving. However, the BE metric tends to have a longer runtime, especially in the median to maximum range. This is due to the iterative nature of the calculations required for a thorough safety assessment. This next bar chart illustrates the runtime analysis for the sensor model, the spawn point prediction, the vehicle phantom agent prediction, and the pedestrian phantom agent prediction. Looking at the data, we see that the sensor model and the spawn point prediction operate quite fast, with runtimes that are well suited to the demands of real-time processing. When we turn our attention to the vehicle phantom agent prediction, we see an increase in runtime. These are more complex computations as they involve predicting the movement of dynamic objects based on numerous possible trajectories. These runtimes, although workable in a simulation environment, exceed the limits of what can be deemed practical for on-the-ground applications where decisions need to be made in milliseconds. In summary, our frenetics occlusion module enhances AV safety by adapting the AV's behavior near blind spots. It identifies and models the movements of occluded traffic participants, allowing for proactive adjustments in driving behavior. The model's adaptability and open source availability catalyze further innovation and refinement within the community. Despite these advancements, we must critically acknowledge the module's current limitations in runtime efficiency. The real-world application of such safety systems demands high-speed processing that our module does not yet consistently achieve. Hence, our future work is clearly laid out. We are concentrating on three main areas. First, we will have a look at fine-tuning criticality thresholds to match specific traffic scenarios, enhancing situational awareness. Second, we see potential for incorporating temporal tracking. This could add another dimension to our predictions. Lastly, and most importantly from a critical standpoint, we want to make significant efficiency improvements. By offloading some of the heavier computational tasks to a more efficient programming environment such as C++, we aim to cut down on processing times. This step is crucial and is expected to bring the system's responsiveness in line with the stringent demands of live, on-the-road autonomous driving. The key takeaway is this: while frenetics occlusion enhances safety in occluded scenarios, our mission is not only maintain but elevate this standard, ensuring that the system can operate seamlessly in real time and every time. As we conclude today's presentation, I'd like to thank all of you for your attention. For those interested in exploring further, we have provided QR codes that link directly to our papers and the GitHub repository where our code is hosted. There is also a link to our lab's website for more information on our ongoing projects. We are excited to share our work with the community and welcome any collaborations or discussions that can drive this research further. If there are any questions, feel free to contact us anytime. Once again, thank you for joining us today.